Welcome to the tutorial on characteristic equation of the flip-flop. There are four types of flip-flops, that is the SR flip-flop, the JK flip-flop, D flip-flop and the T flip-flop. The simplified form of their function tables is given here. The figure A shows the SR flip-flop, figure B shows the D flip-flop, figure C shows the JK flip-flop and figure D shows the T flip-flop. From the function table, we can see that the output Q represents the present value and Q plus represents the next state value. A variation of the simplified function table is called as the next state table, which will be shown in the further tutorial. So let us define what is a next state table. A next state table basically shows the value of the next state of the flip-flop for each combination of the values to the present state of the flip-flop and their information lines. So if you look at this particular table, here we have the various flip-flops which show the present state, that is Q, and the next state, that is Q plus. For each of these tables, appropriate interpretation is that for a given preset state Q and the inputs, the application of the control signal causes the flip-flop to change to the next state Q plus. The algebraic description of the next state table of the flip-flop is called as the characteristic equation of the flip-flop, and this description can be obtained by constructing the K-map for the Q plus terms of the present state and the information input variables. So here is the Karnaugh map for the SR flip-flop, which is shown here in the figure A, and to indicate the invalid condition, we have considered them to be the don't care terms shown as a dash. So in this particular Karnaugh map, we have used the function table which is indicated here, wherein S, R and Q are considered as the variables and Q plus is considered as the output. So I have plotted Q here, S and R here, and S and R are having various combinations 0, 0, 0, 1, 1, 0, 1, 1. So as we recall, S and R combination equal to 1, 1 will yield us an invalid condition. That is, both Q and Q bar will be equal to 0. So if I have to write the expression for Q plus from the function table, I can see that for a condition of S equal to 1 and R equal to 1, irrespective of Q being 0 or 1, I obtain Q plus to be the don't care term. So from this particular function table, I yield Q plus to be equal to S plus R bar Q, that is obtained by combining the various groups in the Karnaugh map. So this particular group of 4 variable Karnaugh map will give me the expression S, whereas this group will give me the expression R bar Q. In a similar manner, we can obtain the various characteristic equations for JK flip-flop, D flip-flop and T flip-flop from the function table that I have indicated here. So from this particular Karnaugh map, I can say that for a case of SR equal to 0, 0 is included to make sure that both S and R signals should not be equal to 1. simultaneously for the proper operation of the SR flip-flop. Next, let us look into obtaining the characteristic equations of JK, D and T flip-flop by simplifying using the Karnaugh map. So here I have the function table wherein I have represented the present state and the next state. So I will require a 3 variable Karnaugh map, and I have represented the JK variables here and Q variable here. So I can form two groups by mapping the min terms onto the Karnaugh map, and I obtain the expression as JQ bar and K bar Q. So the final expression for the JK flip-flop will be JQ bar plus K bar Q. Moving on, to obtain the characteristic equation of the D flip-flop, I have considered the table wherein I have represented the present state and the next state. Here I will require just a 2 variable Karnaugh map because at the input side I have just D and Q. So if you look at the function table, you will observe that for a combination of 1 0 and for a combination of 1 1, I obtain Q plus to be equal to logic 1. So from that, when I map the variables onto the Karnaugh map and group them, I obtain the characteristic equation Q plus to be equal to D. Next is the characteristic equation of the T flip-flop. Again, I have two variables T and Q, and the min terms are obtained for a combination of 0 1 and 1 0. So I obtain the expression as TQ bar and T bar Q. So the characteristic equation Q plus can be represented as T XORed with Q. So finally, to summarize, here I have represented all the characteristic equations of all 4 flip-flops, SR, JK, D and T flip-flop, and I have also shown you how to obtain these characteristic equation from the function tables by representing the present state and the next state.